Hello, welcome back to this course on structures, stereochemistry and reactivity of organic molecules and intermediates, a problem solving approach. In the last session, we were discussing the aldol reaction, and we have seen that in the aldol reaction, what happens? There is basically possibility of formation of four stereoisomers, basically two diastereomers, two diastereomeric pairs. I can say that one can be called a syn and pair, and the other is the anti pair. Okay. Now, the genesis of that formation of these four isomers, basically this I did not mention in the last lecture, is that the reaction that is happening is basically an enolate and another carbonyl system. Okay. So, this is the enolate, which is basically the donor component, and this is the acceptor. So, that is the donor component and this is the acceptor component. So, this comes back, attacks the carbonyl. Okay. Now, you know that there is there are two kinds of phases that are possible across a double bond or across a carbonyl. Okay. Like when these electrons are coming here and attacking this carbonyl. So, obviously, this carbon has a phase. So, either it is approaching the carbonyl from the top face, or it can provide its the phase which is at the back to the carbonyl. Similarly, the carbonyl can also have two kinds of phases, like the ray phase or the psi phase, you know that. And so, depending on which phase is reacting with what, you get a type of stereoisomer. Like if it provides a ray phase, and if also the ray phase is involved here, so you have a ray-ray combination, or you can have a psi-psi combination, that is possible. See, this is basically that gives you one diastereomer as a pair, as an enantiomeric mixture, and the other one is the ray and psi, or psi and ray. So, this gives the other diastereomer existing as an enantiomeric pair. Okay. So, that is basically the genesis. It is the phases, the different types of phases that can add up together, and that gives rise to four stereoisomers. Okay. And we have seen in the last lecture that there is a natural preference for the syn diastereomer, because of the fact that in the transition state, the alkyl group of the aldehyde wants to adopt an equatorial orientation in the Zimmermann-Traxler 6-membered chair-like transition state. Okay. Now, let us try to see that how we can, but that all about the diastereo selection. Let us try to find out that how to introduce enantiomer selection or enantiomer selectivity in an aldol reaction. Now, there are different ways to do that, because in aldol reaction there are two components. One is the enolate and another is the acceptor molecule. Okay. The enolate, if both are achiral, then what you can get is only diastereo selectivity, like the syn selectivity, but you will not get any enantiomer selectivity there. Okay. If there is, if you want to introduce enantiomer selectivity, you have to either introduce start with a chiral enolate and an achiral aldehyde or carbonyl compound, or a chiral or an achiral enolate and a chiral carbonyl compound. Okay. Or you can have both as chiral, that means your enolate is chiral, your carbonyl compound, the acceptor is also chiral. So, that you can basically you are trying to amplify the asymmetry, that is possible, but there is no that is not mandatory. You need one chirality at least in one of the components. On the other hand, there is another possibility that you can use a catalyst to do the aldol condensation, like TiCl4 what Mukayama was using. So, some kind of catalyst that you use, but the catalyst itself is a chiral catalyst. Okay. So, if you use a chiral catalyst, then you can have a this aldol condensation which can be enantiomer selective. Okay. So, these are basically the 4 possibilities. Okay. The chiral catalyst can be metal catalyst or it can be enzymes also, because there are enzymes which do aldol condensation, okay. Aldolase enzymes, okay. And that also gives rise to high level of enantiomer selectivity. Okay. So, these are the 3 possibilities, your chiral enolate or chiral acceptor, or you can say chiral donor, chiral acceptor, or you can have both chiral or you can have chiral catalyst. Okay. So, these are the possibilities. We will consider the only one where this is a chiral enolate plus achiral acceptor. Okay. Achiral acceptor. Now, chiral enolate, what sometimes reactions have to be taken, have to be carried out between only achiral substrates, means your enolate is achiral, your acceptor is also achiral. But the reaction, interesting part of the reaction is that the reaction itself generates 2 stereogenic centers. Okay. Now, in that case, how to induce enantiomer selectivity. So, what has been one particular very well known strategy is what is called chiral auxiliary based approach, chiral auxiliary based approach. So, in that case what you do, that when you have the enolate, so at the enolate level you attach something, a temporary group which has got chirality, built in chirality. Okay. You attach that built in chirality, so that the whole thing becomes chiral, and now you add this to the acceptor, to the acceptor, do the reaction, get the aldol, but remember the aldol will have attached with this chiral appendage that you have started with from the enolate, and then after the reaction what you can do, you can take this off and get the aldol. So, that is the strategy of a chiral auxiliary based method. Okay. Now, different chiral auxiliary groups are available. Okay. Chiral, see, when you talk about any asymmetric synthesis, you have to have some chirality somewhere. It may be chiral catalyst, it may be chiral auxiliary, whatever it is, or you may start with a chiral ketone also, chiral carbonyl compound. The question is, what is the source of these compounds? What is the source? The source is from nature, because nature provides us molecule which are chiral molecules, and usually they are available when they are produced, they are mostly produced in one chiral form. Okay. And from that chiral pool, what we actually get our either the chiral auxiliary or the chiral catalyst or the chiral substrate. All these are possible. Okay. There is another common approach for asymmetric synthesis called chiron approach. That means, you start with a chiral compound and then subsequently develop new chiral centers, new stereogenic centers, but that stereogenic center chirality will be controlled by the existing chirality. Okay. So, that is what is called chiron approach, but here it is auxiliary based approach. This auxiliary is also a chiral compound which is available from natural sources, and the one that I am going to describe is actually obtained from amino acids, because amino acids are available in one particular chiral form and mostly in the L form. Okay. D forms are you can get it, but they are much more costly. Okay. So, what famous scientist Evans did, see, he made a auxiliary based aldol condensation, which is extremely successful. So, what was the method? The method was basically that you have suppose you have a compound like this, it is an amide type, but this amide is basically hooked as a chiral auxiliary. Okay. So, if you look at this molecule, basically this is nothing but some activated carbonyl compound plus NH oxazolidinone, and there is a substituent, a group here, and that depends on the type of amino acid you are starting with, and also the configuration will depend on the if you want to make it an L compound, then basically you have to see whether the R group is alpha or beta. If this is 1, that is 2, and that is 3. So, 1, 2, 3. So, yeah, this is right. So, that is your L compound. So, this is the starting source is an L amino acid. So, R could be isopropyl, that means it is valine. R could be methyl, it could be alanine. R could be benzyl, that means you are starting with phenylalanine. So, depending on the, if you want more steric bulk, so you use benzyl like phenylalanine, or you can use isobutyl, isopropyl, that will be valine. So, these are sterically more bulky, or even you can have methyl, that is alanine, but that will definitely give varying degree of enantiomeric excess at the end of the reaction. So, this is basically the chiral auxiliary that Evans made from amino acids. See, this is the amino acid. If you reduce the alcohol by diborane, say borane THF, you can in one step you can reduce it to the alcohol, and then this amino alcohol can be reacted with a carbonyl compound like CO, Cl or Cl. This is your phosgene, that is possible, or you can react that with OET, that is. So, you make this oxazolidinone as your chiral auxiliary, and then react that with an activated acid, and you get this amide. Okay. So, this is basically your starting point for the formation of the enolate. So, as you add now, here he used a particular compound, dibutyl boron triflate. Okay. Dibutyl boron triflate will form an enolate like this. Sorry, O double bond O N. Okay, now there are two types of enolates which are possible, either this or you have the other possibility. Okay. So, the way the reaction was done, so the enolate that you get was basically the one where this is, so that is 1, that is 1. So, that means this is your Z enolate, Z enolate. Okay. So, that is what you are getting. Now, there is a reason that why you will get this molecule, because there are two hydrogens here, and this is kinetically formed. If you treat this at minus 78 degree, you will get the loss of that hydrogen, which will lead to this enolate. Okay. Let me just again check, double confirm that this is the enolate that is formed. Yes, that is the enolate, especially when R is equal to say methyl. See, okay, you can actually equilibrate this enolate by to the thermodynamic enolate if you do it, if you allow it to equilibrate, allow it to warm it to room temperature, so that it can equilibrate to the E enolate. Okay. But the way it is done, that it is kinetically controlled, so you get the Z enolate. Okay. So, this is the enolate form, that is what is going to react with an aldehyde now. Okay. So, let us do that. Now, I know that this reaction, when I add RCHO, that reaction, make it R1CHO, that reaction will go via the Zimmermann-Traxler model. Okay. And Zimmermann-Traxler model basically what? Demands that this will be the, now instead of lithium, you have boron here. Okay. You have boron, and then you have this carbonyl, carbon, and here you have the formation of the carbon-carbon bond. Now, the syn selectivity demands that your R1 group should be on this side, that is the syn selectivity demands that. Okay. So, the hydrogen will be on that side, and here depending on the geometry of your enolate. So, that means that your R, if R is methyl, make it methyl, suppose a particular example. So, the methyl will be here, hydrogen will be there, and this is your that chiral auxiliary. Okay. This is your chiral auxiliary. Now, you can write this in two fashion. If you write it in this fashion, let us see whether the R group is now alpha or beta. If this is 1, that is 2. If R is that one, then R has to be beta, because that makes it L, because all natural amino acids except the cysteine are S. So, that is that has to be S configuration 1, 2, 3. So, that is S configuration. So, this is one possibility, this is your butyl. Okay. The other one is, so this is the other transition state is this one. You do not change anything here, because that has to be, that is demanded by the syn selectivity, that the R has to be in the equatorial position. This is your N, just you rotate this. So, now this is R, this is your carbonyl, this is the oxygen. So, the this oxazolidone ring, that will either adapt this orientation or it can adapt the other orientation, where the carbonyl will be on this side. Okay. Now, according to Evans, what happens is that because of these two conjugations, this will be delta negative. Okay. And here this oxygen is also delta negative, negatively charged. So, there is there will be repulsion, this is also delta negative, especially this oxygen. So, all these negative charges will repel this oxazolidinone not to adapt this conformation, but to adapt the other conformation which is shown here, this one, where the carbonyl is just the opposite to the carbonyl, this one. Okay. Now, this is number 1 point, that conformation of the oxazolidinone. The number 2 is that in this case the enolate is coming from the back side, okay, from the back side, and the aldehyde is coming from the front side, from our side. Okay. And you have to now check the orientation of this alkyl, of this group, the substituent which is at the attached to the R group. Okay. This time this R group is alpha. Okay. That means this is okay, that the R group is actually behind and your molecule is now approaching from this side. So, there is no interaction with the R group. On the other hand, had there been that this is the preferred conformation, then the R group would have been on this side and the aldehyde will have lot of steric hindrance to the approach of this to approach the enolate from the side of the R group. Okay. Again I repeat, first of all the oxazolidinone adopts this type of conformation and not this one, that is because of electronic reasons. Okay. Next is the approach of the aldehyde. The aldehyde should approach to the enolate in such a fashion that the side chain of the oxazolidine group should be away from the approach of the from the side, should be away from the side from where the aldehyde or the carbonyl group or the acceptor group is approaching. Okay. Now, the way it has been drawn is perfect. This carbonyl this R group is alpha. Okay. So, that means this approach what is shown here is the favored approach. Okay. One thing, another important point we should remember, that the existence of this axial butyl group at this position, in addition to this axial oxazolidinone, that actually further reduces or further enhances the syn selectivity of this reaction. Because now if R is axial, then it will suffer not only from diaxial interaction from the oxazolidinone, but also from this butyl, and that is because of the boron. Had it been lithium, that would have been absent, because boron has another this axial butyl group. Okay. So, then that increases the syn selectivity. So, syn selectivity is enhanced, number one. Number two is your facial selectivity is also there, because it is only approaching from this side, and that leads to the formation of only one compound, and that compound will be CO N. This is the oxazolidinone R, and then OH, and this will be H. Okay. This will be your methyl and this will be your hydrogen. So, this is syn. If you draw it correctly, then OH will be alpha and methyl will be alpha, both are alpha. Okay. So, that is the syn selective and enantioselective selective. So, it is both enantioselective selective as well as diastereoselective selective. But remember, diastereoselectivity selectivity comes from natural origin, but it is still further enhanced. It is still augmented by the existence of this butyl, and enantioselectivity selectivity comes from the oxazolidinone that your auxiliary, and the auxiliary gives the enantioselectivity selectivity to this reaction. Okay. I hope this is clear now. Okay. So, this is the syn selectivity which is there in Evans aldol condensation. Okay. Now, there are a few questions that how do you really remove this group, because that has to be removed, and it will be nice if you can again utilize this oxazolidinone. If you can utilize, because that is another important issue of organic synthesis, that to reuse the system over and over again, so that to make the reaction that sustainable, because economic sustainability is very important step. Yeah, it is not only yield, but whether you are removing certain things and you are just discarding, that is also not very good, and people have realized that. So, nowadays reactions which are very attractive are basically these reactions where you can reuse whatever is coming out of the system. So, what happened if this is treated with lithium hydroperoxide, that means lithium hydroxide hydrogen peroxide, then it has been found, Evans has shown that this chiral auxiliary comes off, it becomes acid, and you can recover this chiral auxiliary and you can reuse the chiral auxiliary. Okay. So, that is one of the brilliant way of doing this. Okay. Now, the question is, now the next question is, suppose instead of this boron, if you have another metal ion like titanium, if you have another metal ion like titanium, then what happens? Then there is a possibility that this can act as another ligand to be hooked into the titanium. Okay. If that be the case, then what will happen? Then there is a drastic change in the course of the enantiomer selectivity of the reaction. Diastereoselectivity selectivity is okay, it remains the same, but enantiomer selectivity will be a problem, because enantiomer selective, at least the product that you got earlier by using the boron triplet will be totally different when you use the titanium. When you use titanium, what happens? First of all, what was found that oxazolidinone was not very effective, but what was very effective was if you make if you make the thio derivative of this, okay, and if you make thio derivative, then what happens that the titanium now, that means the oxazolidinone is basically adopting a conformation which was earlier ruled out in case of the boron triplet. That is what is interesting. Let me just check one thing, then I will whether it is there or not, the titanium enolate. Yes, the titanium enolate is there. Now, this is, by the way, this is syn compound and this is called Evans syn compound. Okay. On the other hand, if you now use, actually this is still oxygen, this is not sulfur. If you use this type of complex titanium enolate, make the titanium enolate and use one equivalent of titanium reagent to do this reaction. In that case, what happened? You get the whatever you expected from the Evans boron chemistry. That means, if you take titanium as one equivalent, then you do not see any change in the product stereoselectivity. That means, the same Evans syn product is obtained. Okay. On the other hand, if you take two equivalents of titanium chloride, okay, if you have two equivalents of titanium chloride and supported by some base like natural base like spartine, then what happens that you get the other. See, the problem is, if you have this complexation formed, first of all this forms when two equivalents of titanium chloride was used, okay, and some base which is spartine, okay, a natural product spartine. So, what happens? This adopts now this type of complexation. So, that now rotates the earlier one which was forbidden, that rotates and forms this titanium complex. Okay. If that be the case, if this is the major transition state, then the aldehyde cannot approach from this side, from the side which is above this plane of the board towards us, because this R group is now facing us. R group is facing us. So, you cannot get this Evans syn product if you have two equivalents of titanium and then forms which actually forms this complex. Okay. So, in that case what will happen? The aldehyde will definitely come from the opposite side, from the side of the, from behind the board, and this one, this thioxazolidinone will come from the side of this, in the front of the board. Okay. So, whatever stereochemistry you got here, that even syn. So, you will get just the other syn compound, syn selectivity will not be compromised. What will get changed is the ultimate configuration of the syn isomer. So, you get even syn in case of boron triplet, and you get the non-evans syn product if you use TiCl4 2 equivalents, and it increases if you use spartine as the base. Okay. So, that is, I think, the chemistry, or the reason is, the logic is sound. The logic is that now the oxazolidone, earlier there was this electronic repulsion. So, that forced the oxazolidone to push the carbonyl on this side, and the R group was going backward. So, the aldehyde could have approached from the front side of the board, but when this is sulfur, it chelates to the titanium, and the R group is now coming towards us. So, the aldehyde will approach from the back side, and that will invert both the stereochemistries, but then you will get again another syn compound, and that will be called the non-Evans syn compound. Okay. So, that is what is the chiral auxiliary based, one beautiful example of chiral auxiliary based aldol reaction. There are many such reactions. I think we will take one more class where we will discuss some of the problems, because we have not drawn the stereochemistry very carefully. We have just kept it in the Sawhurst projection formula, but we will convert it into the zigzag, the antiform, and then we will show all the products, but that we will discuss in a problem solving session. So, we hope that we will take another, definitely we will take another class, while all the problems which have been which are generated by our discussion through all these 40 lectures, for 30-minute 40 lectures, we will compile them, and in a 1 hour problem solving session, that is the final session, we will solve all those problems and to clarify any doubt which is there in the mind. There will be definitely, because stereochemistry after all is a complex subject, and proper drawing of the molecule, maintaining the proper stereochemistry is an art in organic stereochemistry, and that will be mastered only if you practice more and more, and if you try to visualize as you grow in your visualization process of 3-dimensional molecule. Okay. So, we will have one problem solving session dedicated to all the concepts that have been discussed in this lecture. Thank you very much.